Hello. Today, I'm going to use the gradient vector to solve this problem here. Find a vector equation, find a vector parametric equation for the line perpendicular to the surface z is 2x squared plus y squared at the point -3, 1, 19. And we're going to say r of t equals blank. We'll fill in the blank for that vector equation. Recall the vector equation for a line is r of t is equal to r naught plus vt, where r naught is some point on the line and v is a velocity vector for the line. Well, we already know that r naught is -3, 1, 19, or I guess more specifically, r naught is the position vector, the vector from the origin to -3, 1, 19. So all we need is v is what? What if we knew v, we'd have it made. Okay, so what we're going to be using is this fact, okay, a normal vector to the level surface f of x, y, z equals constant. Okay, that's a level surface. That's the equation for a surface in three-dimensional space. Okay. At the point, we'll call it x naught, y naught, z naught. The gradient of f evaluated at x naught, y naught, z naught. Okay, the idea is here's some surface over here, and here's a point on the surface. In fact, what is the value of c? C is f of x naught, y naught, z naught. You don't even have to figure out what that c is. All right, I got this point on this surface. I got this normal vector here. It's perpendicular or normal. Remember, they're kind of the same word. And orthogonal, they all mean the same thing, basically. Orthogonal, normal, and perpendicular to the surface. Okay, so the important thing here is we need to figure out what the function is. So we're going to let, remember that's an important word in math, let f of x, y, z be, right, it's a function of three variables now. So it's going to be 2x squared plus y squared minus z. So this graph, that surface is, the surface we're interested in is, in fact, I'll do it even in our set builder notation. The surface we're interested in, x, is a set of all x, y, z, such that f of x, y, z equals 0, right? So I brought this all over. Okay. By the way, I'll tell you, at the end, I'll quickly talk about a different way to do that, to do this problem, but this is probably the easiest, okay? So that's the important thing to realize, that this equation written that way is the level surface of a function. And if this had like a z squared or a z cubed or something else where I didn't have it solved for z, I'd really have to do it this way. Now this is actually this is the graph of a function from R2 to R. This is a function f, but this f here maps R3 to R, right? I've defined this function f of x, y, z. So it takes in three variables, x, y, z, outputs a real number, right? So here's something like, it doesn't actually look like this, but we don't have to know what it looks like. That's the great thing about all of this calculus stuff, is that we don't actually have to draw the picture. It's good to know what it looks like, but let's see. I'm going to erase the question, data. I think we can probably do it. can probably do it in that little space up there. So here's a function with 3 variables. So grad f y, z, we got to do that before we can find grad f at -3, 119. So grad f at x, y, z is, here's the function. It's going to be 4x is the first component, 2y is the second component, and -1 is the third component. So that velocity vector we want is going to be grad f. Sometimes I put the arrow over the grad, sometimes I don't. Let's do it here. Is grad f at -3, 119. And that's just at that point. That is equal to -12 to -1. So right? So here's the surface. This normal vector to the surface is the gradient at the point -3, 119. And that's also the velocity vector for the line. So again, think of Tinkerbell flying through space, leaving your fairy dust. That's how the line is traced out. And at t = 0, Tinkerbell is right at the point -3, 119. She's going off in the direction of the normal vector to the surface. Okay, so that right away, we have the 2 bits. We got r, no, we got the v vector. So we have r of t is the vector -3, 119. -12 to -1. And I can, at least if you're watching me because you have this as a web work problem, you can just enter it into web work in exactly that way. All right. Let's leave it at that. I'm not going to do it, but I'll tell you the other way you can do this is, since this is a graph of a function, you can find the equation or an equation for the tangent plane to this graph. Okay, and after you find the equation for the tangent plane to the graph involving partial derivatives, then you can manipulate things and find what a normal vector to that plane is. And then when you found the normal vector to the plane, you'll find it's going to be -12 to -1, or you might find it's 12, -2, +1. It doesn't matter, right? Any scalar multiple of this v will work. In fact, I checked it. WebWork will actually accept this answer with any scalar multiple of that thing. I know that some people have put in square roots. They normalize it, make it a vector of length 1. You don't have to do that, right? Okay, remember, billions and billions of different R of t functions will trace out the same line. All right. Well, I'll see you. Good luck on this problem. I can stop.